Welcome back to The Deep Dive, the show where we take a stack of sources, articles, research, and our own notes, and distill them into the essential knowledge you need to be truly well-informed.
Glad to be here.
Today, we're plunging into a topic that has, well, fundamentally shaped every single building around us. I mean, everything from ancient mine shafts right up to the skyscrapers we see today.
That's right. We're talking about fire.
Exactly. For centuries, this primal force has been just a relentless influence, literally dictating the very codes that govern our built environment. And you think about the catastrophic lessons learned, from the Great Fire of London that reshaped an entire city.
The huge turning point.
To, well, more recent tragedies like Grenfell Tower, which
Yeah.
really forced us all to reevaluate every assumption we had about high-rise safety.
Absolutely. Tragic but vital lessons.
Fire has always been this force that, on one hand, enabled early human progress, but at the same time, it demanded constant vigilance and, frankly, radical innovation in how we design and build.
It really did. And that leads us to our core topic today. The crucial, often unseen, science of fire engineering and life safety.
Unseen is the right word.
It really is. This is a discipline that operates silently, invisibly almost, weaving layers of protection into the very fabric of our structures. And it's all born from a profound respect for fire's destructive power.
So this deep dive, it's going to be a journey, right, through how we design to withstand this force.
Exactly. We'll trace the fascinating evolution, revealing the profound lessons embedded in our structures, lessons often learned the hard way, etched into history by the flames themselves.
Right.
We're going to see how human ingenuity has continuously risen to meet this challenge, turning disaster into design. It's quite a story.
And our mission for you, our listener, is to explore this critical engineering discipline. We're going from its earliest, most reactive responses.
Like just throwing water on it.
Yeah, basically. All the way to the highly sophisticated predictive approaches we see today. We'll unpack the fundamental principles of fire engineering, understand the intricate dynamics of how fire actually behaves in a building,
which is incredibly complex,
and examine the indispensable roles fire engineers play in making our increasingly complex world not just habitable, but genuinely safer.
Couldn't have put it better myself.
So let's get started on this deep dive into the unseen heroes of our built environment.
The foundations of fire safety. Prescriptive codes and historical lessons.
Okay, so our story, it begins not with blueprints, but really in the raw struggle of early humanity. Let's look at humanity's early encounters with fire, even before modern construction, to really get a feel for its dual nature.
It's fascinating stuff.
Imagine ancient miners, deep underground. They're using fire not just for light and warmth, but as a tool, right? A brutal but effective tool to cleave rock.
Yeah, our sources describe them packing dry wood and sticks, shaved down fan-shaped, which easily take light into hollows within the rock face.
Fan-shaped, that's specific.
Right, and they'd ignite these. The intense heat would cause the rock to expand and crack, making excavation possible. It was a powerful technique for material extraction.
Really pushing forward human capability, enabling early civilizations to grow.
Absolutely. But the dangers were, well, immediately apparent and frankly horrifyingly real.
How so?
This process, as our sources grimly note, produced fetid vapor, and the shafts or tunnels are emitting fumes.
Ugh, fetid vapor. Doesn't sound good.
Not good at all. And this isn't just about, unpleasant smells. This highlights a very early, very visceral awareness of the dangers of smoke and influence to health, often lethal.
So it wasn't just the heat or flames getting them?
Often not. Miners would succumb to these invisible byproducts long before the flames themselves. It was a stark lesson. Fire's threat wasn't just physical destruction, but also silent, insidious suffocation.
Wow. So this ancient awareness of smoke as a killer, that's still fundamental today.
Absolutely fundamental. It underpins so much of modern fire safety design.
And even back then, alongside using fire, there was this need to fight it, right? To control it.
Exactly. A foundational human need to combat its destructive potential. Even in these early rudimentary settings, our sources tell us about equally rudimentary but vital fire suppression techniques.
Like what? Buckets.
You got it. In case a workshop or a facina caught fire, they had readily available buckets of leather in which water is carried for putting out a conflagration.
Leather buckets. Okay.
And, surprisingly, even a brass pump with which the water is squirted out to fight the blaze.
A pump. Really? That early.
Apparently so. It's not just about putting out a fire, it's about that basic human instinct to protect what's built, preserve life, salvage resources.
It shows an early, powerful recognition that fire, while useful, needed to be controlled.
Precisely. And that active intervention was a necessity. These simple tools, they represent the very first steps in a long, long lineage of fire protection.
So, what's truly fascinating here is how this basic understanding, fire is useful, fire is dangerous, smoke kills, we need to fight it. How did that translate into, like, actual building choices?
Yeah.
Especially after big disasters.
That's the key transition. This fundamental understanding, particularly after catastrophic widespread disasters, think the Great Fire of London, though our sources refer more generally, it directly translated into much more sophisticated building materials and design choices.
Okay.
Take the Great Rebuilding that swept through Northern European house construction during the 16th and 17th centuries. This wasn't just, a new style.
Not just fashion.
Not at all.
Yeah.
It involved a massive, deliberate transition to masonry, using bricks and stone, moving away from the predominantly wood construction of earlier eras.
And this was specifically for fire safety.
Explicitly and urgently aimed at better fire resistance and ensuring greater structural longevity. It was a direct response to devastating urban fires that could just wipe out entire towns built of timber.
Makes sense. And did it work? Did those buildings last longer?
Massively so. The choice of material had undeniable implications. Our sources make a direct, compelling contrast. Conventional, stick-built houses, what we might call standard light timber frame construction today.
Like most houses now.
Sort of, yeah.
Yeah.
They had an average lifespan of about 75 years.
Yeah.
Relatively short, really, for a structure.
Okay.
But timber frame buildings, specifically those properly constructed with massive, protected, and often exposed wood members, could last at least 300 years, and some over 1,000 years old survive even today.
Wow. Over 1,000 years.
It's incredible. And this isn't just a quaint historical fact for architects. It speaks to fundamental, hard-won insights into structural resilience and the inherent fire performance of materials.
So how does massive timber resist fire better? Seems counterintuitive.
It does, right?
Yeah.
But it's about how you build with it. Massive timber, when treated correctly, actually provides a level of inherent fire resistance through slow charring. The outside chars, forming an insulating layer that protects the inner core of the wood for a significant period.
Okay. So the char protects the structure inside.
Exactly. It shows an early, perhaps intuitive understanding that how you construct with materials profoundly impacts their ability to resist fire and endure.
So from those raw early lessons, smoke, basic suppression, choosing materials wisely, a big shift happened. We moved from just reacting to fire to actively prescribing how to build against it.
A critical turning point, absolutely.
How did these insights, often forged in disaster, come together into what we now call prescriptive fire codes?
Well, these historical lessons, whether for those huge city fires or the dangers in early industries, they directly led to the development of prescriptive fire codes.
Okay, prescriptive codes, like a prescription from a doctor.
Sort of. Think of them as a rules-based approach to building safety, like an extensive instruction manual meticulously crafted over centuries.
Got it. A rule book.
Exactly. Instead of relying solely on intuition or experience or just reacting after a disaster, these codes set specific, detailed requirement for construction. They tell builders exactly what materials to use, how thick walls need to be, the minimum sizes for exits, what active systems like sprinklers need to be installed.
All to achieve a baseline level of safety.
Precisely. It's about standardizing protection, ensuring a predictable minimum level of safety based on all that cumulative knowledge and, frankly, past failures.
So how do these codes work? How do they break down a building?
They really dissect it based on various factors to figure out the safety requirements. The very first step, for instance, is occupancy classification.
Meaning what the building is used for.
Exactly. Is it residential, like a house or apartment building? Is it an assembly space, like a concert hall or stadium? Commercial, educational, industrial. This classification is foundational.
Why is it so important?
Because it immediately dictates a whole host of safety requirements for the entire building or specific sections. It influences everything from the maximum allowable floor area per person, the total number of people allowed, the number and width of exits needed, even the type of fire alarm system required.
So a hospital would have way stricter rules than my house.
Vastly different and more stringent requirements, yes. Precisely because of the varying risks and, importantly, occupant vulnerabilities. People in a hospital might not be able to evacuate easily on their own.
Makes sense. What else do codes look at?
Another absolutely critical factor is the height and number of stories a building can have. Generally, codes impose maximums on these dimensions.
Because taller buildings are harder to escape from and fight fires in.
Exactly. They inherently present greater challenges for evacuation and firefighting. However, it isn't always a rigid, absolute limit.
Oh, how so?
Codes often offer a direct trade-off. If you install an approved automatic fire sprinkler system, you can often significantly increase those allowable limits for height and area.
Ah, so sprinklers buy you more height.
In essence, yes. It's a clear incentive built into the rules to adopt enhanced active safety features. The code recognizes that while a taller building carries more inherent risk, a robust sprinkler system can mitigate that risk by tackling fires quickly at the source.
Allowing for greater architectural ambition, I suppose.
Precisely. Furthermore, these codes define different construction types, each with varying levels of inherent fire resistance.
Okay, like what kind of types?
Well, to give you an example, Type 2 IA construction requires passive protection of all elements of the structure.
Passive protection, what does that mean?
Simply put, it means every major structural component, your columns, beams, floors, even exterior walls, is individually fire-rated. Imagine wrapping each essential bone of the building in its own fire-resistant armor.
So if one beam gets hit by fire, it won't collapse right away.
Exactly. It's designed so that even if exposed to fire, it won't fail for a specified duration, maybe 1 or 2 hours, giving occupants critical escape time and firefighters a stable structure to work within.
Got it. And you mentioned Type IIB.
Right. In contrast, Type IIB construction allows unprotected, non-combustible building elements.
So still non-combustible materials like steel or concrete.
Yes, generally.
Mm-hmm.
But in Type IIB, there's less inherent fire resistance required for the structural components themselves. It relies more on the non-combustibility of the materials, rather than specific fire-rated assemblies for all elements.
So it's a spectrum of safety levels.
It demonstrates a spectrum of prescribed fire safety levels, yeah. Tailored to different building uses, risks, and, let's be honest, economic considerations.
So it sounds like an incredibly robust system built on layers of protection. But here's where it gets really interesting, at least to me. Even within these non-combustible construction types, like Type TIA or IIB, you might be surprised that some combustible materials are actually allowed. How on earth does that work? How do they manage that apparent contradiction?
That's a fantastic question, and it really speaks to the nuance required in fire engineering. It's not as simple as no combustibles allowed. The key principle here is that these combustible materials, even within a largely non-combustible structure, must be of limited quantity and used under defined conditions where they will not contribute in any large measure to compromising the desired level of fire resistance in the structure.
So small amounts, carefully controlled.
Exactly. It's not a free-for-all. Think of it this way. Maybe some decorative wood trim or a specific type of flooring might technically be combustible, but if it's minimal in quantity, contained, and doesn't provide a continuous path for fire spread, it might be permitted.
Are there exceptions for specific things?
Yes, there are specific exceptions, for example, for certain aggregates within concrete or specific fire resistance materials that might have a combustible component but perform exceptionally well in fire tests.
So they've been tested and proven safe, despite being partly combustible.
Right. These often meet stringent test criteria and typically require special inspection during construction.
Meaning someone has to double-check it's installed right.
Precisely. An expert verifies they are installed exactly as approved to maintain the building's overall fire rating. It's all about careful risk management, not absolute prohibition.
It's almost mind-boggling how much detail goes into this, down to the exact construction of the walls and ceilings around you right now. You mentioned that in fire resistance rated or non-combustible construction, the rules get incredibly precise.
Oh, absolutely.
How do these seemingly minor details contribute to overall safety?
They're anything but minor. These details are absolutely critical for preventing hidden fire spread. Our sources explain that wall and ceiling finishes in fire resistance rated or non-combustible construction often must be placed directly against the backing material.
So no gaps behind the drywall, for example?
Ideally, yes. It effectively minimizes any air gaps where fire could potentially sneak through and spread unnoticed.
Okay, but what if you need a gap, like for running wires or something?
Good point. If there are spaces behind these finishes, maybe created by furring strips for aesthetic or acoustic reasons, those strips themselves must be less than 134 inches deep. That's about 44.5 millimeters.
Okay, so a very shallow space.
Right. And any spaces behind them, they must be filled with Non-combustible, inorganic, or Class A materials, basically. Stuff that won't burn easily or be fire-blocked every 8 feet. That's
Yeah.
about 2.4 meters.
Fire blocked. Like little dams inside the wall?
Exactly like that. Why this level of obsession over concealed spaces? Because a fire can travel incredibly fast through hidden cavities in walls or ceilings.
Right, bypassing the fire-rated barriers you thought you had.
Precisely. It compromises the integrity of the entire structure, or can trap occupants above the fire. Fire blocking acts like those internal dams, compartmentalizing these concealed spaces and preventing fire and smoke from freely migrating vertically or horizontally through a building. These aren't just arbitrary rules. They're precise, prescriptive measures designed to prevent fire from rapidly propagating through concealed spaces. It highlights the incredible attention to detail and the profound lessons learned about fire's insidious pathways that are embedded in our fire codes.
Every single one of those requirements is there because at some point, a fire exposed a vulnerability.
Sadly, yes. That's often how codes evolve.
The fire's journey, understanding dynamics and structural behavior.
What's fascinating here, though, is that while prescriptive codes give us these strict rules about what to build, truly understanding how fire behaves, its dynamics, is absolutely crucial for effective safety.
So not just the rules, but the science behind the fire itself.
Exactly. And we can trace this understanding back to those earliest observations. We talked about simple ignition, like the dry wood and shaved sticks used by ancient miners. That's the undeniable starting point for any fire.
Sure, spark meets fuel.
Right. But in a complex built environment, like a modern building, that simple ignition rapidly escalates into a far more intricate three-dimensional problem. It's not just a flame. It's a dynamic, evolving event that interacts with the entire building, its contents, its ventilation, everything.
And those early miners, as we heard, also had that tragic awareness of poisonous vapor and smoke.
Yes. And this isn't just a side effect. It's a critical, fundamental lesson that has endured through centuries. Smoke is often the primary killer in fires, not just the flames themselves.
That's a sobering thought.
It is. Think of it this way. Flames are a visible threat, but smoke is a silent, insidious killer. It often incapacitates occupants long before fire even reaches them.
How?
It impairs visibility. You can't see the exit signs. You get disoriented. It causes rapid incapacitation through toxic gases like carbon monoxide and oxygen depletion. And it spreads rapidly, often far ahead of the actual fire, making escape incredibly difficult.
So that ancient insight is still a cornerstone of modern safety.
A cornerstone. Modern life safety design emphasizes that fire protection isn't just about containing flames, but crucially, about meticulously engineering smoke control. If people can't see, breathe, or move, they can't escape, regardless of the fire's size.
Okay, that really drives home the importance of smoke control. So what does this all mean for us today, walking through buildings? How has modern design directly incorporated these historical understandings, especially about that poisonous vapor and smoke?
It's been integrated into the very DNA of building design. Today's codes are meticulously crafted to control this smoke. They mandate protected enclosures and protected path of egress travel.
These are the fire stairs and protected corridor.
Exactly. These aren't just abstract concepts. These are the fire-rated stairwells, corridors, and exits designed to remain clear and safe during a fire. These measures implicitly, but very directly, tackle smoke control by ensuring that exit routes remain isolated from fire and smoke migration.
Keeping the escape route clear and breathable.
That's the goal. Providing a clear, breathable path, giving people that critical window of time to escape. It's a direct, unbroken lineage from those early, painful observations of smoke's lethality to the sophisticated safety features in every public building you enter.
Every fire-rated door, every sealed stairwell.
Is a silent testament to this historical lesson. Absolutely.
Okay, so getting people out is paramount. But what about the building itself? You don't want it collapsing on people trying to escape or on the firefighters inside.
Precisely. If we connect this to the bigger picture, beyond just egress, a critical aspect of fire safety is ensuring the building itself doesn't collapse under extreme heat.
Not just protecting property, but buying time.
Exactly. Time for people to escape safely, and crucial time for firefighters to gain access and work within a stable structure. This objective is achieved primarily through fire resistance rated construction.
Back to those rated components.
Yes, providing that passive protection of all elements of the structure. This means the building's fundamental components, columns, beams, floors, are inherently designed to maintain their structural stability and load-bearing capacity for a specified period, even when exposed to intense fire.
They're engineered to withstand the heat for a while.
For long enough, yes. They might char, swell, or simply absorb heat, but they maintain stability long enough for evacuation to complete.
And this comes down to the materials used.
Fundamentally, yes. The intrinsic properties of the building materials themselves are key. For example, our sources note, Portland cement concrete is an excellent material for foundation walls. But beyond foundations, concrete, due to its composition and density, offers superior fire resistance compared to many other materials, even brick in some contexts.
Why concrete?
It's not just its strength against moisture and earth pressure. Its thermal mass means it heats up slowly and retains its structural integrity for extended periods under fire conditions.
Yeah.
Water, chemically bound within the concrete, turns to steam, absorbing a lot of heat energy.
Interesting. What about stone?
Similarly, good hard ledge stone can also outperform brick walls in resisting forces, and it offers natural fire resilience due to its density and composition.
And even everyday things, like steel beams. Engineers look at those specifically for fire.
Oh, absolutely. Even seemingly mundane elements like standard beams have highly quantifiable properties that engineers meticulously consider. These include things like weight per foot, moment of inertia, and section modulus.
Okay, jargon alert. What do those mean in plain English?
Aha, right. Don't worry about the terms themselves. Essentially, these numbers are an engineer's shorthand for how much that beam will resist bending, twisting, or collapsing under immense loads. It's about predicting its stiffness and strength.
Not just for everyday loads, but under fire stress.
Exactly. These properties are meticulously factored in to ensure they can sustain loads, including the unpredictable and extreme stresses introduced by a fire. Steel loses strength rapidly as it heats up, so engineers need to calculate how long an unprotected beam might last, or what kind of protection it needs to last longer.
So they need to know how much fight that material has left when it's being cooked.
That's a good way to put it. Predicting that moment of failure is critical for life safety.
It's incredible. And it's not just the skeleton, the structure. The building's entire skin plays a role too, right?
A vital, multifaceted role, not just in containing a fire once it starts, but also in protecting the interior.
Oh, so?
A tight, thermally resistant envelope encompassing the walls, windows, and roof is not just for energy efficiency, keeping you warm or cool.
Right, we hear about that for green buildings.
Exactly. But it's also meticulously designed to control solar heat gain, conduction or direct heat transmission, and infiltration or leakage heat transmission. This robust envelope acts as a critical barrier.
A barrier against fire.
Yes. It helps contain fire and heat from spreading out from a fire within, limiting oxygen supply, and it can protect the interior from an external thermal assault, like fire in an adjacent building.
So it helps compartmentalize the fire.
Significantly, it can slow internal fire spread by limiting oxygen and containing heat, and it helps prevent fire from easily jumping from one floor to another via the exterior, which is a major concern in high-rises.
And engineers are constantly innovating to make this envelope even better, pushing the boundaries.
Constantly. We're seeing some truly sophisticated innovations integrated into these protective skins.
Like what kind of advanced materials?
Well, consider advanced elements like spandrel panels. Those are the opaque bands you see between windows on a glass curtain wall building.
Oh yeah, I know what you mean.
These might incorporate low emissivity insulated glass units and even things like translucent aerogel insulation.
Aerogel. Sounds futuristic.
It kind of is. These aren't just fancy terms, they're components offering incredibly high insulation value. Our sources note values like R20 plus at center for aerogel insulation, and an average insulation value of the curtain wall is about R8, which our sources say is 4 times better than conventional curtain walls.
And high insulation value helps with fire.
Dramatically. It's not just about your energy bill. It dramatically slows heat transfer. In a fire, this contributes significantly to compartmentalization.
Keeping the fire contained to its area of origin.
Exactly. Buying critical time for occupants to evacuate and for first responders to manage the situation. The more resistant the envelope is to heat transfer, the more effective it is as a fire barrier.
Pioneering safety. The rise of performance-based design.
So we've talked a lot about these prescriptive codes, these rule books.
Yeah.
And they're essential, right? They provide that baseline safety, ensuring every building meets a minimum standard.
Right. Non-negotiable minimums.
But this raises an important question. Are they always enough? Especially for highly complex, innovative, or architecturally unique buildings.
Good point. What about those really unusual structures?
Well, for those, simply following a checklist of rules sometimes isn't sufficient. Prescriptive codes, by their very nature, can be rigid. They might not adequately account for unique architectural designs, Imagine a building with a massive multi-story atrium.
Yeah, how do you apply standard rules to that?
Exactly. Or novel uses of space, or innovative materials. This rigidity can potentially stifle creativity, or more importantly, fail to truly optimize safety for structures that don't fit neatly into predefined categories.
So the rulebook can hold you back, or might not even apply properly.
It can. A building that pushes architectural boundaries often needs a fire safety approach that pushes boundaries as well.
So if simply following a rulebook can be limiting for ambitious projects, what does this all mean for the future of design? How do engineers and architects approach fire safety for these unique boundary-pushing structures?
This is where performance-based design comes in. It's a far more sophisticated and flexible approach, really a paradigm shift in how we conceive and deliver fire safety.
Performance-based, meaning it's based on how the building performs in a fire.
Precisely. Instead of simply following a rule book, engineers using this method don't just apply rules, they prove safety. They utilize advanced modeling and analysis, often sophisticated computer simulations, to demonstrate that a specific design achieves a defined level of safety, even if it departs from the prescriptive code.
So they can break the rules if they can prove it's still safe?
In a carefully controlled and analyzed way, yes. The focus shifts from how you build the specific rules to the outcome, demonstrating with quantifiable data that occupants will be safe and the building will perform as required in a fire scenario.
How do they do that? Run simulations?
Exactly. It allows engineers to literally burn down a building virtually, test countless scenarios, fail safely in the digital realm,
Fail safely, I like that.
ensuring that in the real world, the structure performs exactly as intended when lives are on the line. It's incredibly powerful.
That's a powerful idea, virtually burning down a building to ensure its real-world safety. And it sounds like this forward-thinking approach also aligns with broader project management ideas. You mentioned set-based design.
It absolutely does. This thinking aligns perfectly with principles like set-based design. This is where, instead of locking into one design very early on,
Which is tempting, right? Just pick one and go.
very tempting, but often suboptimal. With set-based design, multiple designs or alternatives can be investigated early in a project's life cycle.
Why do that? Seems like more work.
It is, initially, but it's incredibly valuable. It helps reduce uncertainty and allows you to thoroughly explore trade-offs, such as time versus cost, quality versus cost, risk versus schedule, or schedule versus quality.
So for fire safety, you could explore different escape routes or materials side by side.
Exactly. Various egress strategies, different compartmentalization approaches, alternative material selections, all explored in parallel. It's an iterative learning process where ineffective or suboptimal alternatives are discarded throughout the process, leaving only the most robust and optimized solutions.
So fire safety gets baked in from the start, not just bolted on.
That's the goal. It allows for optimization and true innovation that a rigid rulebook might not permit. You're building in flexibility and learning from simulations before committing to expensive physical construction.
And a core characteristic of this whole approach, whether it's set-based design or performance-based fire engineering, is something we hear a lot about. Resilience. How does that apply here?
It's absolutely fundamental. Resilience in this context is defined as the ability to adapt and respond quickly to unexpected changes.
Changes in the design or during a fire.
Both, really. It applies to the building itself, its ability to withstand and recover from a fire, but also, crucially, to the project team members and organizational processes involved in its creation.
Meaning the team needs to be flexible.
Exactly. If an initial design approach for fire safety isn't as effective as hoped in simulations, or if new information emerges, the team and organization need to be able to learn, adapt, and respond quickly, pivoting to a better solution without derailing the entire project.
So it's about designing for the unexpected and being ready to course correct.
That flexible, responsive mindset is essential for tackling the complex, often unpredictable challenges of modern fire safety engineering. Every building presents unique scenarios and demands tailored solutions.
Now, you mentioned simulations. What's really enabling this shift to performance-based design? Is it computing power?
Computing power is huge, yes. But what's fascinating here is how the digital revolution has provided the engine that truly powers this, especially for fire engineers. Building information modeling, or BIM.
BIM. We hear that term a lot in construction and design.
We do. And BIM is so much more than just a fancy 3D drafting tool. It fundamentally transforms fire safety from a reactive checklist into a proactive, predictive simulation laboratory.
How does it do that?
At its heart, BIM is a comprehensive process involving the creation of digital representations of the physical and functional characteristics of a facility. Think of it as a detailed digital twin of the building.
Okay, a virtual model.
Exactly. And these models are captured, analyzed, documented, and assessed virtually, then revised iteratively through the design and construction process. This virtual environment allows engineers to test and refine fire safety strategies with unparalleled precision and foresight.
Way beyond what you could do with 2D drawings.
Absolutely, in a way that was previously impossible.
So what makes BIM so powerful for this?
The real power lies in its parametric objects.
Parametric, meaning they have data attached.
Exactly. Unlike simple CAD drawings, these objects aren't just static lines and shapes. They are intelligent building blocks. They have rules that can identify when a particular change violates object feasibility regarding size, manufacturability, and other attributes.
So a virtual wall knows it's a wall.
Yes. And it carries data about its fire rating, its material composition, its thickness, even its cost. It's data-rich.
And how does that help simulate fire?
Even more critically for fire engineering, these objects have the ability to link to or receive, broadcast, or export sets of attributes like structural materials, acoustic data, energy data, to other specialized analysis software.
So the BIM model feeds data into fire simulation software.
Precisely. This capability is absolutely critical for simulating fire spread, smoke movement, heat transfer, and structural response under extreme heat. It allows engineers to predict a building's performance with remarkable accuracy and identify potential vulnerabilities long before construction begins.
Okay, let's unpack this a bit more. Imagine a virtual plan room where every single element of a building is connected, quantifiable, visible in 3D. That's what BIM enables. How does this translate into practical benefits for fire safety on a complex project?
It's transformative. These powerful BIM tools automatically extract consistent drawings and reports of geometric parameters, which is invaluable just for documentation, sprinkler layouts, exit corridor dimensions, all that.
But it's more than just drawings.
Much more. Their true strengths for fire safety comes from enabling sophisticated engineering analysis and crucial clash detection.
Clash detection, finding where things conflict.
Exactly. Identifying potential conflicts or flaws in fire safety systems, for instance. A sprinkler pipe running right through where a structural beam needs to be, or an egress path that's unintentionally blocked by an HVAC duct or an architectural feature.
Stuff that would be a nightmare to fix on site.
A nightmare. Catching these issues virtually saves immense amounts of time and money, prevents costly rework, and most importantly, profoundly enhances safety by eliminating design errors that could have catastrophic consequences in a real fire.
And it goes even further, right? I saw something about external parameter management. Sounds technical, but what does it do?
It does sound technical, but it's really about maximum flexibility and data integration across different software platforms. It allows for the control of geometric layouts via spreadsheets, for example.
So you can change dimensions in a spreadsheet, and it updates the model.
Essentially, yes. It means data generated in one design environment, maybe a specialized architectural modeling tool like Rhino, can be used to update models in another, like Bentley architecture.
So different teams using different software can still coordinate.
Right. This integrated data can then feed into a central BIM tool that might have specialized cost analysis, energy analysis, and by extension, advanced fire performance analysis capabilities.
Any real-world examples of this?
Yes. The sources mentioned the Aviva Stadium case study project in Dublin, a massive, incredibly complex structure. There, spreadsheets were used for geometric control and coordination, demonstrating how this advanced performance-based approach, enabled by robust data management, is applied in huge, intricate structures.
Ensuring every component works in harmony, including the fire safety ones.
Exactly. It's all about integration.
And this BIM model, it's not just for the design phase, right? It lives on.
Absolutely. If we connect this to the bigger picture, BIM ensures that the design evolution isn't just a one-off process. The BIM model continues to evolve in the construction phase to analyze and communicate the building process in a virtual environment, including sequence of work, means and methods, logistics, and documentation of as-built conditions.
So it tracks how it's actually being built, updating the model.
Yes, the virtual twin of the building is constantly updated, reflecting reality as it's built. It acts as a dynamic reference for everyone on site.
And then after construction,
it transitions into an even broader long-term role. It serves as a shared knowledge resource for information about a facility, from inception through design to construction, occupancy, and operations.
A living database for the building's entire life.
Exactly. Invaluable data for maintenance, renovations, future safety assessments, emergency planning, you name it.
So who manages all this? Who's in charge of the BIM process?
Given this central continuous role, construction managers, CMs, are uniquely positioned as the central information hub for the project.
Makes sense.
This places them in an ideal position to lead the BIM process, not just manage it passively. Our sources state that CMs have a responsibility to educate the owner and the project team on the benefits, features, limitations, and the implementation process for BIM.
So they're the BIM champions, in a way.
You could say that. They are key in facilitating its adoption, ensuring all stakeholders from the architect to the HVAC subcontractor understand how this powerful tool can be leveraged for better coordination, real-time problem solving, and ultimately superior fire safety outcomes throughout the entire project lifecycle and well into the building's operational life.
The fire engineer's expertise, crafting life safety in complex buildings.
So we've talked about the history, the code's prescriptive and performance-based, and these incredible digital tools like BIM. But let's bring it back to the basics. What does this all mean for you, the listener, just walking through a building every day, probably completely unaware of these intricate systems?
That's the core question, isn't it?
It means that fire engineers are tirelessly working behind the scenes to ensure two absolutely critical things shaping your experience in every public space you occupy.
Right. And this raises that important question. How do these engineers ensure that in the event of a fire, you can actually get out safely and that the building stands up while you do? Their primary responsibility really revolves around these twin goals.
Goal number one, getting out safely.
Exactly. First, they focus intensely on providing a tenable environment for egress.
Tenable environment, meaning you can survive in it while escaping.
Precisely. It means maintaining conditions like breathable air, adequate visibility, and survivable temperatures within designated exit routes. The goal is to ensure occupants can safely move inside of or toward a protected enclosure from the area where a hazardous event is occurring to a place where they may finally escape the building.
Avoiding that nightmare scenario of a smoke-filled hallway you can't see through.
Exactly. Imagine trying to escape a smoke-filled room where you can't see or breathe, where the air is scorching hot. That's an untenable environment. Fire engineers work tirelessly to prevent that from ever happening in an escape path.
And how do they create this protected path?
Achieving this requires fire resistance rated construction and opening protectives on doors or windows. These are the robust fire rated walls, doors that close automatically, and sealed stair enclosures that compartmentalize a building, acting as barriers against fire and smoke.
So the fire stairs, the protected corridors.
Yes. Examples include interior exit stairways and ramps, exit passageways, exterior exit stairways, exterior exit ramps, horizontal exits, which are like safe zones on the same floor, and exterior exit doors at ground level.
And in really tall buildings, these paths can be very long.
Critically, yes. In a high-rise building, these exit paths can be very long, and the code places no distance limit on travel within an exit enclosure itself, meaning a stairwell might extend 50 or 100 stories.
Wow, so that stairwell needs to be super protected.
Absolutely. It emphasizes the absolute need for robust, continuous protection along these extended routes, ensuring they remain tenable and structurally sound for the entire duration of what could be a very long evacuation.
And the detail goes right down to the stairs themselves, right? Even spiral stairs.
Oh, yes. The meticulous detail involved in fire safety design gets down to specific, seemingly minor components. Take spiral stairs. While they can look cool and save space.
They seem tricky to run down in panic.
They can be. Their design for fire egress is strictly regulated because they can present unique challenges during a chaotic evacuation. They must have minimum widths of 26 inches, that's 660 millimeter.
Seems narrow.
It is, relatively, and the treads, the part you step on, can be no less than 304 inches, 171 millimeter, at a point 12 inches, 305 millimeter from the narrow end.
Okay, specific measurements.
Very specific. Plus, risers must provide 78 inches, about 1981 millimeters of headroom, but be no more than 9 1 and 2 inches, 241 millimeters in height.
Why so precise?
These dimensions aren't arbitrary. They're painstakingly determined through research and lessons learned from past evacuations to ensure that even in chaos, the stairs remain usable, people don't trip easily, and they don't become an additional hazard. It's all about ensuring every detail supports swift and safe exit.
Okay, so goal 1 is safe egress. What's goal 2?
Goal 2, hand in hand with egress, is ensuring structural stability during a fire.
Making sure the building doesn't fall down.
Essentially, yes. This is achieved through that passive protection of all elements of the structure, those fire-rated components, and by selecting materials that intrinsically maintain their integrity under extreme heat.
Again, buying time.
Buying precious time. Time for occupants to evacuate, and time for firefighters to enter the structure and combat the blaze without fear of premature collapse. Without this stability, all other life safety measures become somewhat moot.
The protected path doesn't help if the floor collapses.
Exactly. A fire-resistant structure ensures that the very framework holding up the building remains sound, even as the environment around it becomes incredibly hostile. It allows the entire fire safety strategy to function as intended.
Okay, here's where it gets really interesting for Nick, connecting all these threads. When you gaze up at an incredible modern structure, like a massive stadium packed with thousands of people, or a soaring skyscraper that pierces the clouds.
Yeah, truly complex buildings.
You're not just seeing architectural ambition, you're witnessing the culmination of fire engineers pushing the very boundaries of safety design. These aren't simple buildings, they're incredibly complex ecosystems that require ingenuity far beyond just ticking boxes on a prescriptive code.
Absolutely. In these highly complex buildings, fire engineers are not merely applying a standard set of rules. Their role is far more sophisticated. They are orchestrating safety through intricate integration of systems and strategies.
Like conductors of a safety orchestra.
That's a great analogy. Their expertise is absolutely critical in the design of complex buildings like stadiums and high-rises, precisely because standard prescriptive rules might not be adequate for their unique challenges.
Like getting 80,000 people out of a stadium safely.
Exactly. Or dealing with a fire on the 70th floor of a skyscraper. This necessitates the use of performance-based approaches and advanced modeling, allowing them to tailor bespoke solutions to the specific risks, occupant profiles, and architectural characteristics of each unique structure.
And they don't do this in isolation, right? They work with everyone.
Crucially, yes. Fire engineers actively facilitate proactive participation of stakeholders. This isn't just the immediate design team, it involves a wide array of parties.
Who else?
The owner-operator who defines the building's use and risk tolerance, the designer and contractor, critical subcontractors and suppliers, equipment manufacturers for systems like sprinklers and alarms, system integrators who tie everything together.
A huge network.
And beyond internal teams, they engage select third parties, such as building officials, local utility companies, insurers, and sureties.
Why involve insurers and officials so early?
To ensure a truly holistic approach. Everyone's input, concerns, specialized knowledge are addressed from the earliest stages through construction and into operations. It's about building a consensus around safety, recognizing that a chain is only as strong as its weakest link. Getting buy-in early prevents problems later.
And BIM helps coordinate all these people.
Through the power of BIM, as we discussed, fire engineers ensure unparalleled project coordination. They can seamlessly incorporate information from subcontractors' shop drawing submittals into the central model, making sure every detail fits.
And they keep running that clash detection.
Continuously. Identifying conflicts between, say, a sprinkler pipe and a structural beam, or a ventilation duct and a fire-rated wall virtually long before it becomes an expensive and dangerous problem on site.
Saving time, money, and enhancing safety.
Definitely. They also promote the use of an on-site model and a designated BIM integrator in a virtual plan room during construction.
A virtual plan room on the construction site.
Yeah, to address problems and devise solutions efficiently, ensuring that fire safety plans are dynamically adapted and maintained throughout the build process. Proactive problem solving is invaluable.
So it seems like a big part of the fire engineer's job is managing complexity and adapting.
Ultimately, yes. A fire engineer's true expertise also lies in their ability to tailor the project management approach, adapting governance and processes to make them more suitable for the given environment and the work at hand.
Because every big building is different.
Every complex building is unique. Site constraints, programmatic demands, architectural vision, even organizational cultures differ. The fire engineer must be agile, able to customize the fire safety strategy and its implementation to navigate the specific challenges of each individual structure.
Ensuring the highest level of protection no matter how weird the building is.
Exactly. They are problem solvers, strategists, and meticulous, detail-oriented experts, all working together to create environments where people can live, work, and thrive safely. Outro.
So we've journeyed today from, well, ancient observations of fire being used in mines and the earliest sort of reactive building materials.
Leather buckets and brass pumps.
Right, all the way to the incredibly sophisticated digital models that now shape our modern skylines. It's really a testament to human ingenuity and an enduring lesson. While fire is an undeniable, powerful force of nature.
You can't eliminate it entirely.
No, but our response to it can be, and frankly must be, meticulously engineered for safety. This deep dive has shown us how the devastating lessons of history, from the Great Fire of London to more recent tragedies, have been painstakingly codified and digitally modeled to build a safer future.
The discipline of fire engineering really is a continuous act of learning and application. It is constantly evolving, absorbing lessons from the past, integrating cutting-edge technology, all to ensure that our most ambitious architectural visions can also be safe realities.
It's a powerful reminder, isn't it? That behind every fire code, every engineered solution, every carefully planned escape route, there's a deep dedication to protecting lives and property.
Painstakingly built on lessons learned and applied. It's a field born from necessity, driven by innovation, and absolutely committed to vigilance.
Indeed. So the next time you walk into a towering office building, or attend a game in a vast stadium, or even just pause in your own home, maybe take a second to consider the invisible layers of protection around you.
The fire-rated walls, the clear exit paths, the sophisticated systems silently standing guard.
Exactly. And it makes you wonder, what other unseen engineering marvels are we surrounded by, silently shaping our daily safety and convenience?
That's a great question.
We invite you, our listener, to ponder the unseen engineering that underpins your world, making it possible for us to live, work, and thrive in complex structures with confidence.